Good morning. Today we are going to talk about problem-solving strategies. Our learning objectives for this session are the following. We should be able to explain Polya's heuristic, compare a detective strategy and Polya's problem-solving method, and solve problems using Polya's four-step procedure. Let's recall our definition of a problem. We defined a problem as an opportunity for improvement, or the difference between a current state and a goal state. Now, consider this question. Is math relevant? Merriam-Webster defined a problem as follows. It's a question raised for inquiry, consideration, or solution. Or, a problem is a proposition in mathematics or physics stating something to be done. Take a look at this billboard found along Highway 101 in the heart of Silicon Valley, sometime in 2004. Actually, it's a Google recruitment tool. Okay. It reads, first 10-digit prime found in consecutive digits of e.com. So if you recall from your natural logarithmic function, that's the base e, and it's approximately equal to the number 2.7182. The prime number they were asking for is 74274663991. Candidates who made it to that page were asked to solve a harder second problem, which in turn guided them to yet another web page that asked for their resume. Wow! So if you know your math, you get a chance to work for Google. In 1985, Holroyd defined problem solving as a process by which the learner discovers a combination of previously learned rules that he or she can apply to achieve a solution. In 1945, Princeton University Press published a book by Professor George Polya entitled How to Solve It. It was translated into 17 languages. Professor Polya suggested a method to help solve a problem known as heuristic. The dictionary defines heuristic as a rule of thumb, an educated guess, an intuitive judgment, or simply common sense. Professor Polya's heuristic consists of 4 steps. Step 1, understand the problem. Step 2, you've got to devise a plan. Step 3, you carry out the plan. And step 4, you look back or review your answer. Did you notice the similarities between Professor George Polya's problem-solving method and the steps a detective will go through in solving a case? Let's compare the problem-solving language with the detective language. So, instead of understanding the problem, we have to understand the case. What are you looking for? Okay. If you are a detective, you have to investigate the case. Have you solved a similar case before? What are the facts? If you are a detective, you analyze the facts or the data. Which data are consistent with the given information? And then, you re-examine the facts. Do the facts support the solution? Can we obtain a conviction? Pretend you are a detective assigned to the case of the dead professor. So you now think detective as you study the case. The detective Colombo had just arrived in the scene of the crime and found that the professor had been in the lab working for hours. He seemed to have electrocuted himself and ended up blowing the fuses for the whole building. Later in the night, the janitor who came to clean up the lab found the professor's body. Colombo suspected the janitor, but when he was questioned, he vehemently denied killing the professor. He said, "I came to work late. When I got off the elevator, I found the professor dead with his head on the lab table. I wish I could tell you more, but that is all I know." Then Columbus said, "I think you can tell us more at the headquarters." Downtown, under grueling interrogation, the janitor confessed. What made Colombo suspect the janitor? So who done it? I hope you can apply the heuristic to solve that case. Now, Professor Polya suggested some problem-solving strategies. This is not an exhaustive list, but let's look at the more common strategies. 1. Construct a table. 2. Make an organized list. 3. You may look for a pattern. 4. You can guess and check. 5. You may draw a picture or a graph. 6. You may work backward. 7. You can solve a simpler problem. 8. You may act it out. 9. You can set up an equation. 10. You may formulate a model. 11. You may brainstorm. 12. You may restate the problem. The list is not exhaustive, but we can always say adopt a thinking strategy. In many ways, we are using this thinking strategy as a catch-all. This is partly because these strategies are not usually used on their own, but in combination with other strategies. Let's look at example 1. How many palindromes are there between 0 and 1,000? First step, understand the problem. Let's reread the problem to find all the clues and determine what the question is asking us to find. Now, what is a palindrome? In English, palindromes are words or phrases that read the same in both directions. Example, I. Madam, I'm Adam. Never add or even. So, a palindrome is a number that reads the same backward or forward. Example, 34,543, 77, 181. Oh, that's a useful palindrome. It is an alternative oral rehydration solution that consists of 1 liter of water, 8 teaspoons of sugar, and 1 teaspoon of salt. Now back to the problem. How many palindromes are there between 0 and 1,000? Sometimes, a problem is too complex to solve in one step. In that case, it is often useful to simplify the problem by dividing it into cases. Then solve each case separately. Step 2. Plan a strategy. So, let's simplify the problem. First, we find the number of 1-digit palindromes, 2-digit palindromes, and 3-digit palindromes separately. Then we make a list. And then step 3, we carry out the plan. So let's list down the 1-digit palindromes. All of the 9 numbers are palindromes. 1, 2, 3, 4, 5, 6, 7, 8, 9. The 2-digit palindromes. Let's make a list. 11, 22, 33, 44, 55, 66, 77, 88, 99. So there are 9 2-digit palindromes. What about the 3-digit numbers? So let's make an organized list of palindromes from 100 through 999. And we have this list. Then we look for a pattern. So we have how many columns? We have 1, 2, 3, 4, 5, 6, 7, 8, 9 columns. And how many rows? 10 rows. So we have 9 columns, then 10 palindromes per column, and that gives us 90 palindromes from 100 to 999. Step 4, we look back, check our answer. So 1-digit palindromes, we have 9. 2-digit palindromes, we have 9. And then 90 3-digit palindromes. So what is the answer to the original question? There are 100 palindromes altogether between 0 and 1,000. Now let's look at our second example. There will be 7 teams playing in the inter-university sports tournament. Each team is scheduled to play with every other team once. How many games are scheduled for the tournament? So one possible solution, using an organized list and a table, would be this. Another possible solution strategy is by using a diagram. Each of the teams will be represented by points. Or we can use a formula. Remember your combinatorial formula, 7 teams taken 2 at a time. And that gives us 7 factorial all over 7 minus 2 factorial, 2 factorial. And if we expand and cancel the common factors, we have 21. Let's rephrase the problem. If 7 people meet each other and each shakes hands only once with each of the others, how many handshakes will there have been? Well, you can act this out as a solution strategy. Are there 21 handshakes? Let's consider the third problem. It's a network problem. We draw 4 dots that mark the corners of a perfect square. The problem is, draw a minimal network spanning the 4 dots. The parts of it may intersect and you are allowed to use additional dots while drawing the network. Let's restate the problem. Suppose you want to construct roads in order to connect these 4 cities. How do you connect these cities so that the total length of all the roads is minimum? So we plan to minimize the cost of the road constructed. At first sight, it seems that the cross of the 2 diagonals with 1 additional point makes the minimal network. Is it? Would that give us the least cost? If the side of the square is 1, then the total length of the diagonals is square root of 2 plus square root of 2, or 2 square root of 2, or about 2.828. How about this configuration? The least cost will be given by 1 plus square root of 3. That's the total length of the network with 2 points of intersections. That's only 2.732, which is less than 2.828. Albert Einstein, dubbed by Time magazine as the person of the century, has 3 rules of work. First, out of clutter, find simplicity. Second, from discord, find harmony. Third, in the middle of difficulty lies opportunity. So if you have a difficult problem, then you have a greater opportunity for improvement. So how did Einstein manage difficulties? He said, if I were given an hour to do a problem upon which my life depends, I would spend 40 minutes studying it, 15 minutes reviewing it, and 5 minutes solving it. Compare that with Polya's heuristic. Problem-solving skills are among the top 10 skills for the 21st century. The workplace wants men and women who don't panic or give up when things go wrong, but who will seek a way around the problem. So to wrap up, how do we manage problems? First, we define the problem. What is the problem and why is it happening? We develop a plan. What are we going to do? We implement the plan or carry out the intervention, and then we evaluate. Did our plan work? Go on your way rejoicing, solving problems.